Hi, Professor Ghassemi here. In this component of the lecture, we'll be speaking about generalization and smoothing. Generalization and smoothing in the NLP context are methods that we use for correcting sparsity, unknown words, and improving the general use of a language model that we develop. Generalization and smoothing is motivated by the fact that n-gram models do a better and better job of modeling training corpus as we increase the size of n, but they also overfit as n grows large. And this is because when n grows large, we start running into sparsity problems real quick. Not every corpus has every word, and most texts will have some words that are unique to them. So if we train on, let's say, the works of Friedrich Nietzsche and all of his books, there's probably going to be, especially as we start using larger n-grams, some of those grams that never show up in Bertrand Russell's works of philosophy. And so then if you want to take an n-gram model trained on Nietzsche, you might have some challenges when you want to apply it to Bertrand Russell. And that's sort of what motivates the need for generalization and smoothing. So let's think about a very simple example. Let's say that we were interested in understanding what the likelihood is that the following sentence is an English sentence: an apple a day, keep the doctor away. Well, you probably remember this training data from the previous component of this lecture. One of the ways that we could go about evaluating the likelihood that this sentence was an English sentence is by looking here in our training data and saying, hey, let's get the probability of an, and then let's multiply it by the probability of apple showing up, given that it's an. And if you actually look through this text, apple is the only word that ever follows and. So, the conditional probability there is actually 100%. And then I could say, okay, well, now, given that I have the word apple, what's the probability of the word a showing up next? And you can see that apple shows up twice. One time it's followed by because, and the other instance is followed by a. So actually the chance of getting an a, given that the word was apple, is 50%, right? Because it could either be because or it could be a. And you could sort of continue doing this all the way down the line, and you could generate a probability that says the likelihood that this sentence is an English sentence according to some very basic language model that we developed. So what happens now if we change this sentence to say 2 apples a day keep the doctor away? Well, nowhere in that training data is the word 2. So because that sentence never shows up, the probability of 2 is 0. Therefore, the probability of the sentence is 0, which is clearly ridiculous because there's lots of other words here in this sentence that do overlap with the training data set. So in practice, if I wanted to solve this problem, one very simple thing I could do is I could come to my training data over here, and I could simply add an instance of the word 2 and an instance of the word apples to this, so that the probability of 2 would not be equal to 0, and therefore the probability of the sentence would not be equal to 0. And I could sort of run my operation from there forward. Now, this kind of operation is similar to what happens in Laplace smoothing, which basically addresses the problem by assuming that any missing word occurs exactly one time. What I'd like to do to demonstrate Laplace smoothing is show you here a set of bigrams from the Berkeley Restaurant Project corpus. Now, the way that you can read this table is the column there on the left-hand side is, let's say, a given word, and then each of the columns thereafter is the next word that occurred following that given word. So for example, if the word was want, the word to happened 609 times, eat happened twice, Chinese happened 7 times, and so on and so forth. Well, what you'll notice is that some of these are grayed out ones. And these grayed out ones are precisely the Laplacian smoothing that we spoke about. It basically ensures that there's never a non-zero probability that will kind of destroy the ability of the language model to work in odd circumstances. Another one of the techniques that people use to increase the generalizability or use of their models is a very simple approach called back off. We sort of did the opposite of this in the previous module. So remember, we had an apple, a blank keeps the doctor away. And we started off early in the last module saying, hey, let's run through the training data and find everywhere where there's the word a and then some other given word followed by the word keeps. And we found that there were several matches. There was 5. And then we said, hey, let's go and look for where apple A occurs, followed by a given word, followed by keeps the. And you may recall there was 1 match within the training data. And then when we finally brought it all the way out to an apple A, followed by a given word, followed by keeps the doctor, that's when there was no match in the training data. Well, one thing we could do if we ran into a circumstance like this where we weren't able to find a match is to simply back out, right? So instead of demanding that we have 3 tokens on either side to try to figure out what the null was here in the middle, we could just back down to having 2 tokens on the other side when we can't find it in the case of 3. And that's simply what the process of back off describes. Now, in practice, when you're going to be doing smoothing, you're going to be using something called Nessernae smoothing. And the difference between Nessernae and Laplacian is that Nessernae helps adjust the importance of infrequent unigrams in the language model based on the number of contexts in which that unigram appears. If that unigram tends to co-occur with lots of other words, it should be preferred to one that only pairs with one other term. That's sort of the intuition behind Nessernae smoothing. So let's try to understand that by looking at this example. Let's say we were asked to fill in the word in the blank there. I can't see without my reading blank. Well, let's say that there was a number of options, but in the language model that we had trained due to the training data, the probability of the word Francisco following the word reading was higher than the probability of the word glasses. Well, what this model might do then is say, I can't see without my reading Francisco, which is clearly not right. If we wanted to address this, however, we could say, hey, let's think about total number of words that tend to precede the word Francisco and the total number of words that tend to precede the word glasses. So sunglasses might occur, reading glasses might occur. But Francisco is probably only going to be preceded by maybe the word San for San Francisco. And so this probability of continuation, basically how many words before the word glasses exist that map back to glasses, the Nessernae helps account for that. It adjusts that probability and you'd fill in this blank accordingly.